Hello everybody! Today we are going to introduce the concept of inferential statistics and we will see how we can define a parametric model. These concepts are extremely important to understand the topics of point estimation, hypothesis testing and confidence interval. In this video we will use the concepts of random variable, distribution and density function. If you are not familiar with them, look at my previous video Basis of Probability and then come back here. You can find a link on the top right corner. So let's start with the topic of today. The situation in which we want to apply inferential statistics is when we are studying a random phenomenon, like the result of throwing a coin, measuring the height of a person, or the time teenagers watch TV every week. We know that there is a probability model that describes these events, but we don't know which it is. More precisely, in the discrete case, what we don't know is the probability of every outcome, which will allow us to define the probability mass function and cumulative distribution function of the associated random variables. In the continuous case, as we have seen in the previous video, we are interested in the probability defined on the intervals of real number, and the probability density function and distribution of the associated random variables. So, how can we say something about the probability model? The first intuitive idea could be to repeat the experiment several times and then to look at the data we have collected in order to do some guesses about the probability. The idea of inferential statistics is indeed to formalize this procedure. Therefore, we collect a sample and we use it to infer some information related to the probability model of the event. Furthermore, we will be able to measure how much confident we are about this information. For example, in the case of the coin, we can throw it 100 times and then we can use the result to try to give an exact value of the probability of getting a head. But it's quite difficult to guess this exact number. So we can aim to give an interval for the probability of getting a head, or we could be interested just in say if the coin is fair or not. Similarly, in the case of the height, we could use a sample of men in Canada and try to infer something about the average height of men in Canada, or answering the question if the men in Canada are taller than the men in the USA. To give all this answer, we will use the technique of parametric statistics, and the first thing we have to do is to define a parametric model for our event. This will be the focus of today's video. The idea is that, after we have defined the random variable we are interested in, that is a numeric quantity coming from the experiment, we have to restrict the search of its distribution function to a particular subset. We should be able to give a formula of the distribution that depends on just one unknown parameter. We can write this as fx theta, where theta belongs to a subset of R called theta capital. This set of distribution is called parametric model. So we know that there is a value theta 0 such that fx theta 0 is the distribution of the random variable x. For simplicity, we will consider just the one-dimensional case, but in general the parameters can be more than one. As always, for the continuous case, the distribution should be continuous. If we indicate with fx theta, where f is lowercase, the mass function or density function, depending if we are in the discrete or continuous case, we can also use this function to indicate our parameter model, again with fx theta. Let us see some examples. For the coin, it is straightforward to define the parametric model. We can use the random variable that takes the value of 1 for the head and 0 for the tail. We can then indicate with p the probability of getting a head, and indicate the mass function as p to the x times 1 minus p to the 1 minus x, where we know that the parameter p will be between 0 and 1. Now, if we think about the example of the height, we can indicate the value of the height using the real positive number. Indeed, we associate to every person the height in meters. However, we don't know which parametric model to use. So guys, let's see how we can solve this problem. There are mainly three different factors that can help us to choose the parametric model. The first one is a specific theory or some previous experimentation regarding the phenomenon we are studying. The second one is the exploratory data analysis. And the third one is some philosophical principles that are well accepted by the scientific community. Let's see them better on the next slides. Sometimes the knowledge about some intrinsic characteristic of the phenomenon can help us to restrict the models we can use. This knowledge can come from strong empirical evidence, for example, if a lot of data have been collected in the past, or from a specific scientific theory. Let us see an example. Suppose we want to have a model that describes the time we have to wait until an unstable nucleus decays. A known property of this phenomenon is that it has no memory. No matter how much we have waited without seeing it decay, we cannot use this information to help us to predict how much still we have to wait. In mathematical terms, we can say that the probability of x being greater than x plus t, given that x is greater than t, is equal to the probability of x being greater than x. The only distribution with this property in the non-negative real numbers is the exponential distribution. So we have just one possibility for our parametric model. We will consider fx lambda, that you can see on the slide, where the unknown parameter lambda is the inverse of the expected value of the distribution. Sadly, many times the knowledge about the phenomenon is not sufficient to determine the parametric model. So we should collect some data coming from the experiment and plot it in order to get an idea of the distribution. We can check if it fits some well-known distribution. In the example, you can see some data coming from an exponential distribution and a normal distribution. Finally, if we have more parametric models that are good candidates, we can use some well-accepted principle to choose one of them. For example, if we have two candidates models and one of them depends on less parameter, then we should choose this one. Indeed, we don't want to add unuseful complexity to our model. Other times, we could use the principle of choosing the model which is less predictable. That is the one that maximizes the entropy. The idea is that we have to choose the model which makes less assumption about the distribution of the variable. If you are curious, the formula for the entropy are the ones on the slide. Since from now on we are going to speak about samples coming from an experiment, it is worth to fix some concepts. When we say that we consider a sample of size n, we mean that we have considered n realizations of the same exact experiment that are independent. Indeed, there should be no interaction between the different times we repeat the experiment. For example, the outcome of one realization doesn't influence the next ones. For every realization, we consider the associated random variable. So, to indicate this, the notation on the slide is used. We consider a random variable for every realization of the experiment, and we indicate this by x1, xn. The abbreviation IID over the tilde stands for independent and identically distributed, and the function after the tilde indicates the distribution of the random variables. Pay attention that when we want to indicate the specific value of a sample, we use the lowercase letters x1, xn. However, when we want to speak about the distribution of every realization, we use the random variables. They are not constant, since they are a function from the sample space. Now, guys, it's time to see an example of a parametric model in the continuous case. So, we are going to introduce the normal distribution. This distribution is very important. Indeed, a lot of natural phenomena follow it, like the heights. Another reason is because it is connected with the central limit theorem, an important result we are going to see in a moment. So, the normal distribution takes values in the real numbers, and we can write its density function as the formula you can see on the slide. It depends on two parameters, that are the mean and the variance. For a lot of cases, we can use this as parametric model. We can consider both parameters or fixing one of them, because we already know it, and let the other changes. On the image, you can see the example of the density function in the case of mean 0 and variance 1. An important property of the normal distribution is that the mean, the median, and the mode are the same. The value can be easily found looking at the peak of the curve. Another important characteristic is that the density function is symmetric with respect to the mean. If we keep the same variance but we change the mean, the graphic we find is exactly the same, just centered in the new mean. Here, for example, we have taken 1 as mean. On the other hand, if we keep the same mean but we increase the variance, as the example on the slide, where the mean is still 0 but the variance is 2, we have that the peak of the curve is still 0, but the curve is wider. Let's introduce the famous central limit theorem. Let x1, xn be a sample of size n, from a distribution with mean mu and variance sigma squared. Let x bar n be the sample mean, that is the sum of all random variables divided by n. This is still a random variable, coming from the random phenomenon collecting a sample of size n. Indeed, depending on the sample we have collected, the sample mean will get different values. Then the central theorem says that as n increases, the distribution of the sample mean minus the mean multiplied by the square root of n will become similar to a normal distribution of mean 0 and variance sigma squared. From this follows that when we consider large n, the distribution of the sample mean can be approximated by a normal distribution of mean mu and variance sigma squared over n. It is a very powerful result, because no matter what the distribution of xi is, the sample mean will follow the normal distribution. Let us fix the concept with an example. Suppose that we are interested in knowing how many hours per week a teenager watches TV. We can represent the time using the real numbers. For example, 1.5 is an hour and a half, and so on. This phenomenon will have its own distribution that we don't know, with a mean which we indicate with mu, and a variance which we indicate with sigma squared. Then we can collect a big sample, like the data of 1 million of teenagers, and calculate the sample mean. Thanks to the central limit theorem, we know that the value we obtain comes from a normal distribution centered in mu. Since the variance is sigma squared over n, we know that the bigger the sample is, the more likely the sample mean will be near the mean. That was the last topic for this video. So let us quickly recap the concept we have learned today. We have introduced the idea of inferential statistics. We have defined what is a parametric model. We have seen how we can find a parametric model for our event. We have formalized the notion of sample, introduced the normal distribution, and finally we have seen the central limit theorem. Thank you a lot to have spent this time with me. Please leave a comment below. Let me know what you think about the video and what you would like to see in the future. Finally, don't forget to smash the like button and to subscribe to the channel.